Swayam Prabha. Digital India. Educated India.
So let's think of solving this equation. Simple equation. So what is the solution? What are x which will satisfy this? So this will tell x must be 1 of square root of 3 by 2 or minus square root of 3. Okay, agreed? Okay, there are something to discuss about it. We know these natural numbers 1, 2, 3, 4 and so on. What is 3 by 2? Huh? But there is no by in natural numbers, right? We know only natural numbers, right? So 1, 2, 3, 4, 5 and so on. But you have written 3 by 2. So there is nothing called by in natural numbers. So what do you mean by 3 by 2? Yeah, when I tell what do you mean by Albert Einstein, you will say he is a man. Huh? It is a rational number, like that. But what do you mean by 3 by 2? But there is no division. In natural numbers, there is no division. So what do you mean by 3 by 2? All that you have natural numbers is 1, 2, 3 and so on, right? So we write that set as this. Now there is no division. So what do you mean by 3 by 2? It's natural to ask, no? Huh? Okay, in natural numbers what are there? There is no division, but what other operations are there? Addition is there. Huh? So that means, what does that mean? If you add any two numbers, natural numbers, you will get one natural number. That is what it means, right? Some way we have to define how this works. Okay? Is that fine? So we know addition of two natural numbers. Then what else we know about natural numbers? Multiplication also. Let's write like this. So again, it means if you take any two natural numbers and you put one m into n, that also gives a natural number, right? Okay. Then what is subtraction? There is a problem with subtraction. But subtraction, how did you learn? Go back to your childhood. When you were 3 years old. So you have some 10 chocolates, then you give it to your brother or sister, some 4, then you have 6. So you say this is minus. What I have got is 10 minus 4 equal to 6, right? Now you want to give 11 to your brother. So you say how many are remaining? Now you are telling, at that time remember, when you were 3 years old, you will say 0, right? I have nothing, I gave 1 by 1, counting 10 over 11 I can't give, I thought okay I have 0 now, whether you have got 11 or not I am not worried, right? So if you give from 10, 11, you get 0, that is not minus, but that is also an operation, right? Provided 0 belongs to natural numbers, but 0 is not. 0 is not. So you can give only up to 9. If you have 10 chocolates, you can give only up to 9, in order that it is in the natural numbers, right? You can't even give 10. So that model fails for subtraction. Then what is subtraction? If that model fails, So what do you say? Okay, you go to a shop, your mother has given you some 10 rupees to buy something, the shop fellow tells it is 11 rupees. Okay, but you want to take it urgently. So you say, okay, I will give you later, give me it. So shop fellow agrees, he knows you, so he gives, okay, you take this, you give me later. Then you say that I have to give you back 1 rupee, but I don't have now, I will give it later. Now how much you have? You have still 0, you have given all 10, right? But then you will have to give some day, right? So if tomorrow you come with 5 rupees, you have really 4 rupees only, because you have to give that minus 1. So that's how you have learnt minus. But they are not, that is not minus operation, that is minus of a number, right? That is minus 1. It is not subtraction. It is just the number minus 1, right? So now you agree to have minus 1, minus 2, minus 3, right? That means natural numbers are not sufficient to even work in simple situations like this. Okay? So we invent new numbers, represent them, then new thread. Okay, we will call them integers. So we will have 0, we will have 1, 2, all those natural numbers. Also we will have minus 1, minus 2, all those. Huh? Okay? So now we will call them integers. Now let us look back. What operations are defined there? Division is not defined. Subtraction is defined. Now we are happy with subtraction. Multiplication is defined, right? But we have to define it. It is not defined yet. Multiplication of natural numbers is defined. That we know. So how do you define multiplication of integers? It should be consistent with earlier one, right? Huh? So you have defined like 2 plus 3 equal to 5. Now you have 2 minus 3. So how do you define that? I have only plus 1, 2, 3, 4. These plus I know. Now how do you define plus over the integers?
Well, you are moving along the number like some number of steps.
So it is 2 plus minus 3.
So you are going this way in the number line 3 steps.
There is no number line. That we have to do again something. From here, how do we define minus?
If you are saying 2 minus 3, you start at 2, then you go to the previous one, then you go to the previous one, go to the previous one, do that 3 times, you will get to 2 minus 3.
So some ordering, you need some ordering. The way it is written, that is the order. So that means 1, next comes 2, next comes 3 and so on. So here 0, next comes 1, next comes 2, but before it also there are something, right, previous to it. Previous is minus 1, previous is minus 2, some ordering is assumed. Without order, you can define 2 minus 3, 2 plus minus 3. How do we do?
Represent it as 2 minus 3.
Hmm?
From minus 3 you can go to steps forward.
No, in the integers we don't have minus, right? Till now we have not defined. We are trying to define the first operation plus itself. Then other things will come, right? So first operation itself we are in trouble.
So plus operation, when we have our order, it is moving from your starting point, which is 2, and it is moving in some direction. In this case, it's the negative direction, and it's moving 3 steps.
So once you have the order, you think of both the orders at a time, next and previous. You can have only one type of order, say only next. Why? If m is next to n, n is previous to m. Only one side is enough, right? One direction is enough.
But Sir, then where will we start the images on both sides? Is different. Where will we start?
Where will you start? This is both the sides going. So it doesn't matter where do we start, right? Does it matter?
Sir, if you are defining it only with next,
Huh.
and if you start at 4,
Huh.
then you can say 5 is next to 4.
Next to 4.
6 is next to 2. But then you will have no way of
Then 4 is next to 3. We will not say 3 is before 4. We will say 4 is after 3. It's only language.
You're defining 3 using 3.
Yes, it is there. 3 is there. So we can define. Right? But what is the meaning of this order? When you say it is order, you mean 2 equal to 1 plus 1, 3 equal to 2 plus 1. So next to means plus 1. Right? So previous to it,
Minus.
okay, we are fixing it, but it's not clear. Why should be minus 1? It can be minus 5.
Previous number is some number, that number plus 1 will give you a prime number.
So you have to define minus 1.
So minus is
But minus 1 we have put already here. So what is the meaning of defining it again? We have already minus 1.
So can we say minus is the direction, plus will be come 0 if we have a point, then plus will be the direction to the right.
Yes.
And minus will be direction to the left. And
Yes.
based on that you can find the magnitude.
So both the directions you will need. But there is a connection between left and right. If m is left to n, then n is right to m, and conversely. So 1 is enough. Yeah. If you take the lower number, so minus 3 is smaller than 2. Minus 3 is smaller than 2. That you are assuming. That is defining the order. If you have the order, then yes. Right? And what you will be assuming with the order? Not just next to, but something else you are telling. What you are telling? Minus 2 is less than 1. Minus 1 is also less than 1. Whichever this side will be less than that. Right? And also, if minus 1 is less than 1, minus 2 is less than minus 1, then minus 2 is also less than 1. So that also you are assuming. Lot of things we are assuming, right? Just to define plus. Is it required to assume so many things? Well, it is fine. With order you can define. Without order? Huh?
It's not an assumption, right?
Then what it is?
So it's like a fact, right?
No, I would have written like this. I have 0, I have 1, then I write minus 1, then I write 2, then I write minus 2. So there is a starting point now. But that is not the order you want to show, right? Some different order you have written. Why you have written this way?
But we are defining like this.
Huh? It is a set, na? In a set you don't have any order, right? It is just a set of points. It doesn't matter who is sitting where. It is a set of students. Okay. So in that case, there is no ordering in the set. We just wrote it for convenience because I have to write in some way. But there is no order there. Okay. But you have one order in the natural numbers. Without order you can't do anything now. That's what it shows, right? So okay, let us look at the ordering of the natural numbers. So what is the ordering? First number is 1.
Add 1
Next number is 2. Next number is 3. Next number is 4, and so on. That is the ordering. Okay. So that means m, then comes m plus 1 for any natural number m. That ordering is assumed there. Fine. So with that order also we have some other assumptions, like if m is greater than n is greater than p, then m is greater than p. That is also assumed in that order. Is that okay? You can define those orderings without assumption also. Like you define m plus 1 is always bigger than m. That is my definition. Definition of bigger than for any m. Right? Is that okay? You can define the order even if it is not there. Just starting from plus 1.
Sir, but if you don't have order, how will you define m plus 1?
How do you define m plus 1? So, what we are calling m plus 1 is not m plus 1 really. We are writing it m plus 1. We say 99 and then 100. I do not know what is the 100 has relation with 99. All that I know 100 is bigger than 99. It is next to it. So, all that we know in natural numbers is what is next to what. That is enough. 1 is the first natural number, then what? There is something called next to, right, or successor. So, who is succeeding, who is coming next? So, there is something, some order is there or some relation like next to, it is really a function, right. From 1 there is a next to, then whatever is that number there is again next to, right. Whatever is that number then there is next to. That is enough for us to define natural numbers, right. So, we can define natural numbers now. We will say 1 is a natural number. Then we will say if m is a natural number, then next to m is a natural number. So, next to I will write as S, successor of n. So, these are enough to define natural numbers now. Next to m. That is our interpretation. All it says there is a function from natural numbers to natural numbers, right. That function is 1 to 1.
What does it mean to be next to?
There is no meaning. We are just defining something next to. We will think in our mind next to means okay, after this it is there. We will write it at the right of it. We will write it after this. Otherwise, it has no other meaning.
So next to is defined, right?
Next to is assumed.
So it is defined. Like here I have 99 apples, here
Huh.
100 apples.
But there is no 99 na, in natural numbers.
So why not? There
Why not? We are starting with 1. Only 1 is a natural number, nothing else.
you have, let's say I have 1 apple, you have 2 apples. You, I have,
But I do not have 2, na?
sir,
I do not have 2.
so you make,
I have only 1.
so you make the numbers first and then do operation, right?
No.
Notation given to
See, when we started, we thought that 1 is a natural number. We know 2 is a natural number, 3 is a natural number, and so on. What do you mean by and so on?
the increasing progression.
What is increasing?
You add 1 and 1.
What is add?
You, sir, you
See the problem? Something you are assuming in mind. You have not told it to me. Right? So, once I go on asking, you are telling one by one different words. How many words I will go on doing that for defining natural numbers?
Sir, but at that point you can stop and say, okay, fine, this.
Where to stop? Up to 100?
No, sir.
Then? It is just a symbol for me. I don't know what is 1. It's just a symbol.
Yes, sir, so we're using the notation for the quantity.
Just a notation. You can write alpha. You can, yes. You have to call something, right? You just chalk is a natural number. Okay. Then there is some natural number next to it, duster. Okay.
So are we assuming one to be a natural number or are we defining one to be a natural
We want to define. See, when you say I am assuming that 1, 2, 3, all of these are natural numbers, then you are assuming infinite number of things. Right? See the problem. You are assuming every one of them is a natural number. How to say? You say 1001. Why is it a natural number? I can write it with digits. So that means you take the digits 0 to 9, then compose according to your rules. Just take them sequences, put them together. Whatever you get, that is a natural number. That's your definition, right? But that will not give rise to order. That will not give rise to how to add. That will not give rise to how to multiply. See the problem? Huh? So what we need is a perfect way of telling that this is my natural number. These are the orderings defined there, so that I can work with them. Okay? Got the point? Why we are defining it? We want to point out what are exactly the assumptions from which we will derive something. We are interested in this somewhere else, right? We are starting with the definition itself. Is that clear? So instead of assuming all these infinite things, there are infinite assumptions here. 1 is a natural number, 2 is a natural number, 3 is a natural number. Everything I have to say it is a natural number. Right? Instead of that, what I will say? I will say 1 is a natural number. Start with that. Right? Then I will say there is a function defined over natural numbers. It is S. So S is a function defined on natural numbers, 2 natural numbers minus 1. It is a bijection. Only this much I need. Right? It is a function which is a bijection 1 1 on 2. It is starting from n, ending with n minus 1. 1 is not there in the range. 1 is not a successor of anything. Right? So that is my starting point. So that means it is a set. It is just a set. Even 1 is not there. Now it is 1 is also not there. Right? It is just a set on which there is a function. A bijection is defined, leaving one element from it. Whichever element is left, I will call that 1. Okay. Now 1 is also not there. You are happy? You wanted something, 3, starting from 3. Okay. Start from anywhere, it does not matter. There is 1 to which is not in the range of the function. It is that function that is important. There is a non-empty set. There is at least one element there. Then n minus something is a set. So there is a bijection between n and n minus 1. This much I need. Once you have this function, then you say whichever is not there in the set, I will call that 1. Right? Then I will take S of that I will call as 2. Then I will take S of that 2, I will call that 3. Then I will take S of that 3, I will call that 4. Continue. Now order is defined, everything is defined. Whatever you wanted in natural numbers.
I don't understand taking S of that. I understand. Okay, we are assuming 1 is a natural number. We are taking the successor of that. How can we take the successor of that if we don't know?
That is given. That is our assumption. Main definition is that it is a set, right, where there is at least one element. It is a non-empty set, right, and there is a function on that set.
So S is just we are creating.
Just some function is there. Some function is given. We are writing that as S. There is a function from n to n minus that element, some element.
So how will we tell if this is the correct function to take?
We don't know which is the correct function. We need a bijection. That's all. You can take any other, but from there only your natural numbers will be defined. Take any bijection. From the bijection only your natural numbers will be defined. Right? Is that okay? So it is not the other way we are coming. Suppose you are defining a function t. T is a function. Now t of 1 equal to 5. What is 5? That is s of 1. 4 times s of 1. But s and t are different now. So it can happen that t of 1 equal to 5. Okay, that's all right. But this is a different bijection. So I don't have natural numbers before it. I don't have s. Now with t I will start. So 1 is 1, or that element is 1, and t of 1 I will call that as 2. It's just calling it, that's all, whatever it is.
What we are taking as an assumption, and we are building upon it via
A function.
whole function, then our function is made upon an assumption, right? The whole
Yeah.
function.
Yeah,
Then we can just write from 1, 2, 3 and till infinity we can make
but
that
we are
as
not able to write till infinity, na? That is the precise problem.
so we
That
are
since there are infinite number of things to be written, we don't know how to define infinite number of things. So from a finite means we want to define it.
okay.
So what is that finite means? Just assume that there is a function, there is a bisection from n to n minus 1 of the elements. Then that one of the elements is called 1, s of 1 is called 2, s of 1 is called 3, and so on. It is just renaming them, right? What is? That is minus. That you take away that element from this, whatever remains.
Doesn't the range of the bijection keep changing? Because range of the function, doesn't it change? Because like when you do s of 1, then 2 is not there in the range, right? So then it's not a bijection.
No, you have the function s, then you say something is not in the range.
Oh, so like when at first it's n and 1 is not there. But
One is not there in the range.
yeah, in the range. But
okay.
then when you do s of like 2, then 2 won't be in the range, right?
No, 2 is already in the range because this is s of 1.
But s of 2. So
S
for-
of 2 is 3.
yeah.
That is also in the range.
So 2 is not in the range, right? For
2
s
is
of
in the
2.
range because this is s of 1. So what does that mean? That means, all it means, I am starting with some symbol, right? Or my first symbol to start with, like Bible told, no, let there be light, let there be one. So it is there, some element. Then what I have? I have this. Then I have this. Then I have this. Continues. Now everything is generated from this S only. So again I rename. I will say, instead of always writing like this, I will write this as 2, write this as 3. Basically this much is required. It is a 1 on 2 function. It was not done in your classes? Bijection? Function is known? Function? Function you know. So 1 function? What is a 1 function? Tell it. Listen.
For every element in the first set, that is the domain, you have a unique image for that. So one pre-image is connected only to one image. That is one. And on to is every element in the second set, that is the range. Range should be equal to the codomain, such that every image is associated to some pre-image.
Okay, understood? So that means you have a function, you have a set, you have another set. So a function is simply arrows, right? Like this. Set of these arrows. So what happens? You say it is 1 to 1 if from 2 elements you don't have arrows to a single element. Right? If you can't find 2 elements here, which will have the same image. If x is not equal to y, then fx is not equal to f of y. Right? That will happen. That is called 1 to 1. And it is on 2 if this situation doesn't happen. Whichever element you take from this, an arrow has gone to it. Right? Okay? That is called on 2. So this is 1 on 2. That means 1 is not there. In the image, 1 is not there. Everything else is there. Right? Everything is S of something except 1. So 1 is not there. Everything is S of something. That's all. So it is on 2. On 2 n minus 1. All right? They are just symbols for S of 1, S of S of 1 and so on. We are giving another name to it. Just instead of S of 1 always, we will say it is 2. Let us abbreviate it. Huh. We have not given any operation. We are just defining what are natural numbers. They will come. Okay? Alright? So, we are doing some cooking. Don't go to eat immediately. Wait. Huh? The rice has not boiled yet. Okay. So, you have the natural numbers now, and automatically there is an ordering here. Now, you see the ordering? That next two thing brings the ordering, right? So, that means if you can generate n by applying s many times from another m, then n is bigger than m. Simple, right? So, any s of something is bigger than the earlier. So, automatically ordering comes, and very natural ordering, right? Then what happens? You will define addition. Okay. So, how do you define addition?
Addition is just taking
It is a new operation. New operation we are defining, right? So, what we will do? We will write s of something is that plus 1. That is our definition now. It is just a definition we will give using our s. Fine. So, we will say that, say, s of m equal to m plus 1. So, plus 1 is defined, not plus everything, plus 1 is defined. Right. What is the meaning of plus 1? It means s of that. Okay. Then how do you define others from this?
repeating this.
S of m plus 1 is S of m plus 1 and plus 1.
Say you are defining m plus n. How do you define this? If n equal to 1,
S of m plus n minus 1.
will not jump, wait 1 second. What we have defined is plus 1, right? So, it might come to that case immediately. So, let us take out that case first. So, we will say if n equal to 1, then you have defined it. That is the first step to say, right? So, we will say this is S of m if n equal to 1. Okay? This is the first case, because that is what is in our mind. We have not defined that, we have that in mind. So, we will say m plus n equal to Sm if n equal to 1. So, that in m plus 1 is that. We have just defined, so we will write it here. What is the next thing we have to do? From this we have to generate others, right? So, if n is not equal to 1, then n equal to s of something, right? So, now let us take that case. If n is not equal to 1, then n equal to s of k for some k, right? So, what we do? We will write here it is equal to s of m plus k. Okay. Whatever is that, I do not know what is that, but that defines recursively. It's difficult to understand in the beginning, but it is very natural to define that way. Huh? Yeah, I also do not understand. Okay, look at this. First thing is, I want to define n plus n. So, first I look at n. What is this n? N can be one of these, right? So, if n is 1 in the beginning, then what I do? I will take just s of m. That is my m plus 1. Fine. If n is not equal to 1, then n will be s of something. Say s of k here, s of 3, right? So, what I will do? I know how to define m plus 3. So, from there I am defining m plus 4, right? Because once you know for 1, you know for 2 using this, again you know for 3 and so on. So, this will define. Now understood?
So we are keeping on repeating this operation.
Repeating this operation as many times required. Okay, is that right? So, So this is the way we will define plus in natural numbers. You see, we have assumed all those things from our childhood. Now to express it exactly in language is very difficult. And most of mathematics is concerned with that. Not only what you have thought and this, how to express it correctly. That's very important. Huh? Huh. That's what other numbers are here. Example. Let's take an example. Now, let us try to apply what do we mean by m plus 4. Apply our definition. Now, m plus n equal to 1, it is s of m. But n is not equal to 1, it is 4. So, what will it say? It will say n must be equal to s of k. Right? So, what is this? This 4 is equal to s of 3. Right? So, I will write here s of m plus 3. M plus k, k is 3, right? But what is m plus 3? I don't know. 3 equal to s of 2. So this will be equal to s of m plus 2, right? And what is this again? This is s of m plus 1, because 1 is there. And what is m plus 1? S of right. So now m is somewhere, it is 4. So that means 4 times of that m, 4 times successor of m. So that means from m you go 4 places, m plus 1, m plus 2, m plus 3, m plus okay. So automatically your ordering now comes because of this. Clear? Yeah, we have used this way. It can be used. It can be used this way. If you know for smaller numbers, you know for smaller numbers how to define. So for larger you can define. Right? Using the smaller ones.
So the definition of S of m, you said that basically next to m. What does next to mean?
Nothing. Nothing. It is S of. See, next to is one intuitive idea. This is in our mind. What is the meaning of next to? Now we have expressed through a function. We think that this function has captured the idea of next to, and it has captured in this way. Right? So when you work formally, you will be working formally with S, the function. In mind you will be thinking of next to. Right? That's how it will go. Carry both the things. Express formally and think there intuitively. Right? So like you have the picture and you are describing it by a poetry. So if that picture is captured or not, that is your job to see. Right? So it is that way. When you have formal expression through a function, you will see that yes, intuitively everything is captured correctly. It will go hand in hand. Huh? Okay, is that fine? So that's how you have defined the addition operation. Then multiplication you can define with repeated addition. Right? That many times you go on adding it. M into k means m will be added with itself k minus 1 times. Right? K minus 1 number of plus will be there. Fine? So multiplication will define, fine. Then you have the integers. So what do we do for integers now? There is no previous now.
There exists some n such that s of n is equal to 1.
So that will be another axiom or assumption on the integers, because it is not available in the natural numbers. Right? Like 1, there is nothing previous to 1. Okay. So again,
Yeah, but then you have defined it as there exists an integer such that S of that integer is 1.
And then the second step would be S of some other integer would be S of S of.
okay, again similar way. Fine, but there is a better way. Still there is a better way. Huh.
Can we say that just like how we did for integers saying that 1 is a natural number, if m is a natural number, then S of m is a natural number. The same way for integers, the same two statements except replace natural with the integer and 1 with 0. So 0 is an integer. If m is an integer, then S of m is an integer, and if S of some k is an integer, then k is an integer.
So basically what you are telling, you have to get it as many times as required, it is S of that.
Yes.
But problem will be how many times it is really required.
No, so like how we did for the natural numbers, we said that you can do it infinitely.
Because there is a starting point.
Yes, sir. This time the starting point is
For
0.
integers no starting point, no.
Sir, we are starting with 0 and saying we are defining next
but-
to and previous.
But 0 also will be S of something,
Yes, sir.
whereas 1 was not S of anything. There is a trouble.
Another function
Huh.
you
Okay, it is an extension of that function. We may think of extension of the function. It will be same when it is restricted to n. It is different elsewhere. So to get that formally is a difficult one. Yes.
It's a, can we take from one we can take two functions, one going forward and one going.
Then backward and forward should be same for some.
No, but then we can use one as a starting point for both of them. So we
Huh.
can
So you have a backward one. Let's say it is t. So t of 1 is 0, right? And t of 0 is minus 1. You are thinking, loud thinking, right? Now then, t and s have to be related. No? They are related really, no? When we think intuitively. So that means if t of m equal to n, then s of n equal to m. That condition has to be there. So basically it is an extension of this s. It is an extension of s. But it is now also regressing both the sides, that side and also this side. S inverse of 1 is not defined. How? We have to give another number, is it not? So it is equivalent to that.
If we somehow define t, like you said, then we actually don't need s, right, sir? Because if we want 2, t of 3 will be 2. So then we only will require s.
Same thing. So it is similar thing. All that is captured by telling that there is a function which is an extension of this s. On a subset it is defined like this. Outside this it is defined like this. So that's an extension. Right? Possible? But then you have to define plus and everything from there, as usual. It is a tedious process again, right? So there are other ways, like you define equivalence classes of relations, right? That is also possible. But formally there is a better way. What you do? Just assume that if n is a natural number, then minus n is an integer. Fix the sign minus, that's all. Okay. Do nothing, just fix a sign. If n is a natural number, then minus n is an integer by definition, right? And 0 is an integer. And natural numbers are integers. Just give assumption.
But what does that sign mean?
That we have to explain. Okay. So formally it looks like this now, but then it is nothing because it doesn't say minus 3 is less than minus 2 or greater than minus 2, right? So that has to be defined. Then what will you do? Suppose you admit that minus m's are there. for any natural number m, minus m is an integer by definition. And all natural numbers are integers. 0 is also an integer. You define like this. Then our definition is easy. But then we have to say how this s operates, how this plus operates, and so many other things we have to define. Formally just writing that will not do, right? Formally that is okay, idea is fine. We just formally put a minus sign. We have put it, okay, they are integers. But what to do with them? We have to tell what is the meaning, what is the ordering, and so on. Right? So ordering will be easy. We will say that every minus m is less than every n. Okay? Whenever there is minus sign prefixed, it will be less than unprefixed. Right? And also 0. We will put 0 also. Like this. We will just assume this, an ordering relation.
Then this is just
Not yet over, something else is there. Something else is there, that's it, wait. So what else we will say? We will say minus m is less than minus n if n is less than m.
Can we do the same thing by saying that for any natural number, 0 is less? Yes, sir. Can we do the same thing by saying that for any natural number n, 0 is less than the natural number, and then m plus minus m?
We don't know that plus, no?
No, sir. But we have defined it for the natural numbers. We can
For
extend it
natural
to the
numbers we have
integers.
defined, not for integers.
We can extend it to the integers.
That is what we want. If you assume that, then you want to define integers by assuming the relation, by assuming the operation. But operation needs what is the set on which it is operating. Understood? So first we have to define the elements of the set, then we have to define the operation on the set. Right? So how do we define the elements? We have the natural numbers, then to it we just include 0 and minus of all those things. That's our integers formally. Right? Now we will say the ordering. So what is the ordering? Any two negatives can be compared by looking at them reverse as natural numbers. Minus 5 is less than minus 3 because 3 is less than 5. Right? And then all minuses are less than all plus, all without minus, and 0 also. These two will be sufficient.
Previously also we needed S in order to define the set of natural numbers. So why can we do it there but not over
Now
here?
we have natural numbers, so we don't need it again.
Oh, but
So we are extending it to a bigger set.
okay.
We have already defined natural numbers, right? So we are extending to integers. Then again, why should we go through that process? We will use that. See, it is a very nice principle of science, no? That scientists always stand on other scientists' shoulders. Okay? So already we have defined natural numbers. Why should we redefine it again? Huh?
So the minus sign which we are taking here is an assumption again.
Assumption.
So we still don't know what it stands
We don't know what is it.
Even
just
plus,
a symbol.
Plus also we don't know, it's just a symbol.
Plus is only operation.
Operation.
This minus is not an operation.
It's a symbol.
Just a symbol. Right? We can define all those things through equivalence classes, but that will be again tedious. Instead, we will just formally define like this. We have n, then we take the set of integers. How? Every natural number is an integer, 0 is an integer. If m is an integer, then minus m is also an integer.
So how can we define C? What is C?
Nothing,
Then how can we define
just a symbol. We are working with symbols now, right? Intuitively something is in our mind. We want to capture that, right? So we just define symbols. So what are the symbols? First symbol is 1, next symbol is s, next symbol is 0, next symbol is minus sign. Only this much we need. Through this we generate all integers now.
If we assume that 0 is there, then how do we know it's not there? I mean, how do we?
How do we?
How is it? How do we know it's there? Like, if we're assuming 0,
We don't know. We are putting. We are putting. It is there. Huh.
Sir, can we define the order of integers by using the inverse of the successor function we defined previously?
No, s cannot go beyond 1, no? When you
Yeah,
take
but-
the inverse.
Yeah,
it
but we
cannot
can
go
write
beyond 1.
from n to z.
see, inverse of S will be a function from n difference 1 to n. It's all within 1 n, not going beyond it, right? So whatever you do, it has to be extended. One doesn't come that. So is that all right? So formally we can define the integers this way.
So you said that 0, minus, s, 1, all of these are symbols. So they're different types of symbols. So
There are different types of symbols, yes.
probably you have to say that s is a different symbol from minus.
Yes,
Different symbol from 0, 1.
that we remember.
1 are the same kind.
Yeah, that we remember. Okay? So all that we have is the set of integers now. It could be defined. Then from integers we have to define rational numbers. The same way addition, multiplication can be defined in the integers. It is an extension of same operation on the natural numbers. Right? Just prefix the sign. How to prefix the sign, you have to tell that. Fine? Then that will be defined. Okay. Let's assume that we have defined all those things. What about division? Multiplication is defined, division is not defined. Again, equivalence classes can be used for that. Huh? So that means we want to define something like 3 by 2. We want to define something like this. So how do you define 3 by 2? Numbers between? Huh? How do you want to define this 3 by 2? It will not give an integer, that's fine, right? That's what we think, right? It is a number between 0 and 1. Huh? Then? But there are two integers, 0 and 1. Which two integers you have to tell, right? So 3 by 2 will be between 1 and 2. That is, but it is midway between 1 and 2, not just between. So all those things it should capture. When you define this, all these things it should capture. Not only between just two integers. All those things should be there. How do we define that?
Sir, can we define 3 by 2 as like if you take 3 by 2 whatever it is and multiply it by 2 because multiplication is defined, you'll get 3. No, whatever 3 by 2 is, whatever it is.
We use this to define it. We define multiplication.
Sir.
See, this is really this is correct way of thinking, because minus we have just put something, we don't know what minus is there. Formally you have just put minus, take them as if they are some interesting things, right? Like natural numbers. Similarly, we have the integers now. From the integers, we can think of doing something formally, similar way.
So like as we define the function s, like we add +1. So can we say division is like adding whatever is in the base, you add those quantities the number of times as those in the numerator. So that's basically division.
So that is, instead of adding, you say multiply 2 with it.
So then we'll say multiplication, not
multiplication we have defined.
Okay,
object.
sir. Yeah, multiplying that.
Assuming multiplication we have defined.
Yes, sir.
So what is telling? We will assume something like it is a number. It is that number which, when multiplied by 2, gives 3. That is our idea, right? It may not be an integer. We don't know. So we will assume something else, something extra we are assuming probably, because we know there is no integer which will be multiplied by 2 will give rise to 3. Agreed? It will not give. So our assumption is that something else exists. It is not an integer, but it exists. So that means it exists is a bigger set. We are really making the set bigger now, from Z to something else. But what are those things? They are just formally these symbols, nothing else. Right? So we have in n these symbols. These symbols were there, right? Now what we did? We put these symbols along with those. Some more symbols we have put. Those are again symbols, nothing more. We are putting some more symbols to it, enlarging our set, right? So what kind of symbols we will put? We will put this kind of symbols. Zero is already there, so it can be 0 also. M can be 0 also, right? Or basically this, where M is an integer, right? And n is a natural number. Just put these symbols. They are again symbols. We are just putting those symbols inside that set, and it is a bigger set now. And this set we will call as natural numbers. This set we will call as integers. Now this set we will call as rational numbers. What does it mean by taking these symbols? This symbol means how do you work with that. So our meaning means how do you work with that. That will give the meaning, right? So if you know meaning means what, you say tiger, the word tiger. What is the meaning? You will show it looks like this, right? But now in mathematics it is not just looking like. Whatever is looking like they are put there, right? So the meaning of it will come to say how do you work with it. So how do you work with these numbers? If you multiply that with n, you will get n. That is the way of working with that, right? Is that okay? So formally it is nicely defined without going to your equivalence classes and so on. Then rational numbers will become this way.
So n can also be a negative number, right?
No, we will take only natural numbers.
Only natural.
It will be easy for us. No? You can also say GCD Mn equal to 1. You can say m and n do not have any common factor. That also you can impose. Huh? We will also impose that. Huh? All right.
Why do we consider whole numbers as separate samples?
They are not separate now. Now what happens when n becomes 1, we will identify that with the numbers. That is an identification. That we will define m by 1 equal to n for m in Q totally at a time. Now we can work with all those things.